book. That's really kind of you. Yeah, as you will see from the screen, I've actually changed the title for the talk. This is new work, kind of something that I've been thinking about all years since the book came out, some of the implications of the stuff that I was talking about in the book about the relationship between life and mind, and why the abstraction of artificial neural networks isn't able to capture that connection between biology, neuroscience, and psychology. This is what got me interested in the new field of basal cognition. But as it turned out, as I was sort of working on this paper throughout the summer up and through the autumn, I found that a more sort of foundational issue regarding how we conceptualize medium independence of computation needed a bit more fleshing out. I needed to think through what the precise issues were. So actually the bit on basal cognition and Aristotle just comes up right at the end. I've snuck that in, but most of the talk is about the concept of medium independence and how this is prompted by some new discussions around neuromorphic computation. So I will actually just show you the agenda for today. A lot of the discussion around different kinds of hardware, developing hardware which is more brain inspired, is motivated by the costs of computation, so how energy intensive it is to use AI today. So I'm going to talk a bit about this. And medium independence, as classically understood, treats energy consumption as sort of an issue which is not central to what we're discussing today. But it turned out, as I was trying to think through what's going on with the debate over medium independence, in particular in response to Gualtiero Piccinini, things like these practical issues of energy consumption are actually central to the questions that I had in this debate. So this is motivating me to introduce this new concept in the vicinity of medium independence, which I'm calling practical medium independence. I'll explain what that is in section 2, and then go on to give you this argument as to why brains would not be medium independent in this new sense that I'm talking about, and then finally discuss the implications for AI, bit on basal cognition, neuromorphic computing, and the philosophical implications regarding this Aristotelian framework. So the talk itself should be about 50 minutes, if I don't rush too much, but I was told that there is open-ended time for questions after this session. If anyone wants to hang around, if anyone is able to do that, I'm happy to stay past the hour and discuss further. Okay, right, so this is topical in the press fairly frequently these days. This was an article that I found at the start of the month. There was others even in the same newspaper subsequent to that, about how much energy AI today is consuming, and how this is actually putting constraints on where data centers can be built. The Republic of Ireland is struggling to attract new investment from Amazon Cloud Services because the company is saying there just isn't enough energy in the grid, and even water, which is surprising if you know the country of Ireland, that it rains every day, but not enough water to cool the data centers currently with the infrastructure available. So large language models in particular are hugely power hungry, and this is actually putting a constraint on the development of the technology, given that scaling up, just making bigger and bigger models, is frequently perceived to be the thing that will bring about the breakthrough to artificial general intelligence. The neuromorphic computation is a research field. Articles that I read indicated that this isn't something that's currently in commercial use, but the idea is to look at the energy efficiency of the brain and see if brain-like hardware and software can actually introduce more energy efficiency in artificial systems. So the brain is much less hungry of energy compared to digital computers. So it's normally said to run on tens of watts of power. You 20% of your resting metabolic budget is considered to be what's needed to power your brain every day. It's still a energy hungry organ, given that it's just a smaller fraction of your body's weight, but still you have to fuel the brain on the proportion of the food that you eat each day. So you do not have an infinite energy budget. How this efficiency is achieved is something that's of great interest to neuroscientists and now engineers who want to make more efficient artificial computers. So neuromorphic computation is quite a broad church. There isn't one canonical instance of this, but generally speaking, you can see in a comparison like this, there are a few differences between neuromorphic architectures and classical von Neumann architectures that are salient. So the parallelism, using spiking neural networks, having event-driven or asynchronous computation. A key point for my discussion is that neuromorphic computation, as is developed so far, uses the abstraction that the signaling in the brain is electrical signaling. There hasn't been an attempt so far to actually apply chemical signaling, neurochemical signaling to any artificial neuromorphic system. So the abstraction is that all of the processing in the brain is going on between neuron spiking, and the rest we can abstract away from. There is experimentation in sort of different materials. So most neuromorphic hardware uses silicon-based metal oxide semiconductors, but there's these experiments in novel and inorganic materials. This is one example given there, where using polymer-based materials, some kind of peptides which they're using to try to replicate what ion channels do, changing the electrical permeability of a membrane. So what I'll be talking about so far when I introduce this concept of practical medium independence is related to feasibility studies of computation. So there's a whole field of computational complexity, which in an abstract mathematical way looks at whether a particular program, even though it's computable, can actually be completed within the bounds of energy, space, time available to people. So if you have a program which needs a computer the size of a planet and amount of time, which would be the age of the planet Earth, in order for the program to finish to completion, that for a large enough problem size, I should say, this isn't a nomologically possible application to run, so this would be considered unfeasible. Computational complexity normally looks at, if you like, the scaling of the amount of runtime of a program with the size of the things in the problem set. So I'm not going to be talking about that in the technical sense, but what I will say is that this notion of practical medium independence is inspired by, say, what we need to think about are notions of feasibility, and this is really philosophically interesting as well. I'm interested in, if you like, real world economic and practical constraints. So within the energy that is reasonably available to people given current technologies such as nuclear power. So this is a photograph here of 3 Mile Island, the nuclear power station in Pennsylvania, which is famous for there was a partial meltdown decades ago, but it was still running until fairly recently, but it closed down because the energy providers in the area didn't want to pay the rates that were being charged for nuclear power here. But apparently Microsoft has recently formed a contract with this company to recommission the power station just because they need a lot more electricity for their data centers. So given real world, not science fiction technologies are within the horizon of what looks to be possible in the near future, absent like completely radical breakthrough technologies like unlimited energy through cold fusion. So I'm interested in these kinds of constraints. Okay, so first I'm going to talk about the standard notion of medium independence. The background to this is just a very simple idea that what physical computers are devices which implement mathematical formalisms. So you have this distinction between an abstract mathematical description of a computation, which would be a Turing machine or an artificial neural network or a finite state automaton. And the question of implementation asks how this links to a physical device, which we would say is running this very same computation. So we're familiar with the software versus hardware distinction. And Hoagland has this well-known definition of medium independence, which says that a concrete system is medium independent if what it is does not depend on what physical medium it is made of or implemented in. Of course, it has to be implemented in something, and moreover, that something has to support whatever structure or form is necessary for the kind of system in question. But apart from generic prerequisites, nothing specific about the medium matters, except perhaps for extraneous reasons of convenience. In this sense, only the form of a formal system is significant, not its matter. So this notion of a formal system appears in his other book on artificial intelligence, where he describes formal systems are independent of the medium in which they are embodied. In other words, essentially the same formal system can be materialized in any number of different media with no formally significant difference whatsoever. This is an important feature of formal systems in general. I call it medium independent. So he goes on to define computers as interpreted automatic formal systems. And formal systems are a wider class than computers. He gives the example as the game of chess is a formal system because it can be implemented in an endless array of different media. It can be simulated in a computer. It's still formally the same game of chess. It's simply defined by tokens and the rules that operate over tokens. In contrast, a game of football is not a formal system because the medium in which it's embodied changes the nature of the game. So if you change the pitch size, the pitch surface, all of those factors are crucial to what a game of football is. So the point would be that a game of football within in a computer simulation would not be a game of football, whereas a game of chess in the computer is just as much a game of chess. Piccinini, in various writings, and this is the most recent example, has also used the notion of medium independence quite heavily. So for him, it's been a essential component of what computation is, that it be medium independent. In the recent book with Anderson, he draws this contrast with multiple realizability, pointing out that it's sometimes confused with medium independence, but pointing out that medium independence is an even stronger condition. It occurs if the effect or input-output relationship that defines a multiply realizable property is itself multiply realizable to the point that it is defined solely in terms of degrees of freedom and their organization. If so, then the same higher-level property can be realized within different physical media, so long as they possess enough degrees of freedom that they're organized in the right way. So there is a constraint on a physical system that can embody a medium independent formalism, which is that there's enough degrees of freedom, i.e. different parts of the system and connections between them, such that it can map onto, if you like, the different parts of the formal system, like the chess pieces and the ways that they move around. But if you think of a multiply realizable device like a mousetrap, there are physical constraints on what materials a mousetrap can be made of, because mice themselves are physical entities, and so because of that interface at the input-output level with a physical entity, that brings in more physical constraints. But the point of with medium independence, you don't even have that physical constraint at the input-output relationship. So Piccinini argues that neural computation is medium independent, and one of the reasons he gives for that, I should mention firstly that he considers spiking to be a medium independent form of signaling. He says just the rate and the timing of spikes is what matters to the coding, and because rate and timing are medium independent properties, then spiking is medium independent signaling. He also uses the example of artificial neural network models of the brain, which are he takes to be replicating the same formal process as goes on in the ventral stream of the primate brain in this instance, and yet housed in a very different physical substrate, a digital computer. I would read you out a quote from that text, but I don't have it in front of me because of the full screen here. So anyway, that's the point he's using with these examples like this. Okay, so in response to Piccinini's previous book, Neurocognitive Mechanisms from 2020, I wrote a commentary that arguing that neural computation is not medium independent, making an empirical case against this view. Very much similar in spirit is this nice paper from Rosa Sal from 2022, criticizing the notion of multiple realizability as applied to brain processes. What we're both really interested in is the fact that so much of what the brain does, the signaling, the information processing, is going on with chemical signaling. So spikes are an overlay to that. Neuroscientists like Sterling and Laughlin have argued that spiking evolved in order to solve the problem of long range transmission of signals. Chemical signaling works at close range, like the scale of synapses and within intracellularly, and cells that are connected to each other, or more diffusely as hormones diffusing. But again, having targeted long range signaling is what spikes enable. But there's so much that is going on in terms of chemical signaling that if you ignore that, then you're missing out on a large part of what the brain is doing. And arguably, chemical signaling, it would be bizarre to think of that as medium independent, because chemical signaling works by the specific shapes of particular proteins and the binding affinities interacting with one another. So to say that chemical signal could be implemented with different chemistry and that would not matter to what it's doing just doesn't fit. So that was our point here. But Piccinini has responded to this, and also Zoe Drayson in an article forthcoming in Mind and Language argues that this argument rests on a mistake about what's being claimed with medium independence. So as Drayson writes, if the brain performs computations via its electrical properties, then the brain implements a formal system on the assumption, discussed above, that computation has a formal definition in terms of the mathematics of computability theory. And formal systems are medium independent, even if the physical properties which implement the formal system are not. By comparison, our digital computers implement medium independent formal systems, even though the CPU switches are not themselves medium independent. So the point would be that, okay, a chemical computation, let me rephrase that. The point would be that a computation that in the brain is implemented in chemistry, that computation could still be deemed a formal system according to the mathematics of computability theory, and in principle that same computation could be implemented in an electrical process or a mechanical process or whatever. That is in principle medium independent, even if the brain implements all this stuff with chemistry. But there's some worries about this view, about why we should think of the brain as implementing any kind of formal system. If you think about digital computers, they were invented specifically to implement formal systems. So the abstract Turing machine preceded the actual physical von Neumann machine. But there's no formal system that preceded the evolution of the brain. So Corey Maley and Daniel Williams have both raised worries about this, saying that computational descriptions of the brain are models devised by neuroscientists and they're abstractions from actual neural mechanisms. And this is a point very sympathetic to what I was writing about in my book, The Brain Abstracted, that we should understand the status of neural computational models as abstractions away from all this rich complexity of brain details. But, and this is the key conceptual point, the existence of an abstraction in the sense of an omission, this is what scientific models are, does not imply the existence of an abstraction in the different sense of a formal system, a mathematical abstraction. And this argument that artificial neural networks are formal systems that are implemented either in machines or in brains really seems to confuse these two notions of abstractions. However, it's a common view, so many people adhere to the view that the brain implements formal systems and that the best neurocomputational models approximately capture these, and that these formal systems are medium independent by definition. So therefore, you get to this point that in principle, this formal system could be implemented in a physical system utterly unlike the brain, even if it's not feasible, even if it would take a data center the size of Asia to implement all of these computations that occur in chemistry in the brain, because the digital hardware is less processes this less efficiency. You might need this massive impossible data center to do that, but in principle it's medium independent. That would be the thought. But I find this a kind of very unhelpful position to end up in. It's unilluminating. I'm calling it degenerate medium independence because I think it just takes us down into this irrelevant blind alley. So it equates the existence of an abstraction in the sense of omission with abstraction in the sense of a formal system, which is a mistake. And then it implies that, well, if there's a formal system, then there's medium independence. And medium independence implies that this is implementable in alternative media, though the alternatives may be so demanding in space, time, and energy that it's not feasible. And I think this is an irrelevant conclusion. So what does it matter if in principle we could replicate brain computations in this impossibly large data center? It doesn't mean that anyone is ever going to be able to do this. And so asking questions about the real world possibility of brain-like processing in artificial systems, this is an irrelevant conclusion. So this is what motivates me to introduce this different notion called practical medium independence. And I'll give you the definition of it. I'm going to say that the functionality of a system is practically MI if and only if there is a formal description of that system which can feasibly be implemented in a fundamentally different material substrate. And this description is rich enough that it accounts for all the functional capacities of the system that have been empirically ascertained. By a fundamentally different material substrate, I'm looking at the difference between classes of chemistry. So inorganic materials, as we find in standard computers, versus organic carbon-based chemistry, organic but not alive, versus in vivo biochemistry, which would be the chemistry possible using living cells, which is what the brain has. So to give you an example of how these ideas sort of fit together, I will mention this example of a physical system and a formal description that comes from Maley's forthcoming argument. So I've borrowed his figures and this notion of a turnstile being described by a formal system, which is a finite state automaton. I should point out that I'm not saying that the turnstile is practically medium independent. A turnstile as a device is like the multiply realizable mousetrap. It has to interface with actual physical things, which means that it's not a candidate for medium independence in Piccinini's sense. But I'm just using this example to describe, to tell you how this notion of a abstract model is being aligned with a abstract computation. So you have this physical turnstile, and what you want to do is describe it in an abstract way, in the sense of a model which omits most of its physical details. And this is what you see on the bottom left here. So you can describe the turnstile as operating according to these different components, causally related in different ways. And then you can do this further thing of mapping that first abstraction onto a formal system, which is the finite state automaton, which is an abstraction in that mathematical sense. So what this notion of practical medium independence wants to get at is the question of whether there is a abstraction in the first sense of omission, which is rich enough to account for all of the behavioral complexity of the physical system, that also maps onto a formal description, which can, in principle, not in principle, can feasibly be implemented in quite a different kind of physical substrate. So why care about PRAC-MI? So if brain functionality is not practically medium independent, i.e. it's practically medium dependent, then there's this really important implication that human-like AGI is not nomologically possible. By human-like AGI, I'm assuming here that this would be the duplication of the brain's computations in some other very different substrates. If the brain is not PRAC-MI, this will not be feasible to implement. The point would be that the only way to efficiently implement the brain's computation will be in a medium which has the chemistry of the brain, and therefore you can't run it in a digital machine. So that would be a very big reason why we should care about PRAC-MI. I think scientifically it's interesting because what it's doing is it's tracking the independence or reliance of the functionality of the system on the specific physical properties of the implementing medium. So what was wrong with or not helpful about this other notion of medium independence, the standard one, is that it didn't allow you to track this thing because it was sort of baked into the notion of medium independence that there is no medium dependence. But whatever a computational system is, it is by definition medium independent. But actually, for issues of feasibility, the implementing medium is really important. So if you care about feasibility, what you're really interested in is the way that the computation itself, the efficiency of the computation, depends on what's going on with the physical substrates. Though Aronson, in this introduction to computational complexity for philosophers, points out that many people have just thought that computational complexity and all of these feasibility questions that he is going through in his paper have been philosophically uninteresting. And it's true that most of philosophy of mind has been really focused on these in principle questions from computability theory. things like the Turing Church thesis, which has been really central to how machine functionalism developed. But as I say, I think there are really important issues coming up now, both philosophically and scientifically, where we need to start thinking about feasibility. And Thagard, in this 2022 paper, is someone that's been doing that. That came out in Philosophy of Science, so if you like, an energy consumption argument against substrate independence of functionalist theory of mind. And there's also work amongst people that do mathematical computational complexity studies on AGI and artificial neural networks. So that's the reference there. Okay, so to give you some examples of practically medium independent systems. So how it turns out is that the functionality of analog and digital computers is practically medium independent, though it strikes me that digital computers have a wider range of alternative media. The thing about analog computation, and I'll say a bit more about this in a moment, is that it sort of, in order to perform computations, it relies on certain properties of the system, the physical realizer, which can be implemented in different chemistry, I think in most cases, but it's more tightly bound together. I wouldn't say that practical medium independence is in any way essential for something being a computer, because it strikes me that quantum computers would turn out to be practically medium dependent if they are doing things so quickly that there is no other kind of physical system, class of physical system, which is able to feasibly implement the computations that quantum computers implement. But to bring us back to the brain, artificial neural network descriptions of brain areas, like the one I showed you before of the ventral stream, would satisfy one, because they can be implemented in different media. They're abstract enough descriptions of brain processes that they can also be implemented in digital hardware, but they wouldn't satisfy two. So they're not rich enough to actually capture all of the functionality of a brain area like the ventral stream. A formal description of a brain area that mapped all of the molecular chemical signals as well as the electrical ones could potentially satisfy two, because if it was emitting so little detail in this extremely rich molecular model of the brain, presumably it would encapsulate all of the causal processes that make cognition possible. But as Rosa Saar would argue, it would not be feasible to implement this system in any other kind of chemical substrate, because if you look at, the runtime of even very detailed even detailed but sort of small scale simulations of chemical processes, they have a huge runtime in digital machines. So that would not be feasible to do that. This is just to illustrate some of the richness of chemical processes that we're talking about, but I'll skip over that in the interest of time. So the key point is that practical MD/MI is about the status of abstractions in both senses of omission and mathematical abstraction and how they relate to one another. Digital computers are prac-MI because a description which abstracts away from all properties of the physical instantiating system other than its degrees of freedom still offers this complete description of the functionality. So you have this nice alignment with abstraction in the sense of omission, very sparse abstraction, aligns with the abstraction in that mathematical sense of just being a formal system. And that was part of the design of digital computers. That's what they're supposed to do. There's this open question for neuroscientists about how far they can abstract away from the actual molecular properties of the brain and still map to a formal descriptions that capture an acceptable amount of functionality. So the view that you need all of the rich molecular detail to capture all of the functionality of a brain area would not be agreed on by all neuroscientists. Many would say optimistically that an abstraction to electrical signaling, as with artificial neural networks, or maybe spiking artificial neural networks, adds some more detail, but not going all the way down to describing the brain's chemistry would be sufficient to encapsulate the brain's cognitively relevant properties. So I think this is a really interesting question for neuroscience. It's an empirical question in some extent. People just need to build lots of different models and see how much of the variance of the data and the behavioral complexity of brain areas they actually are able to capture using different grades of abstraction. But what I want to do in the next part of the talk is actually give you more of a first principles argument about why we should expect the functionality of the brain to be quite heavily dependent on the physical substrate, the physical medium. So more down the path of what Rosa is saying about the rich molecular complexity being highly relevant to the brain's overall cognitive capacities, and so why we should expect this open empirical question to be going more in that direction as the evidence accumulates, as opposed to expecting that very sparse abstractions will be sufficient to capture the brain's repertoire. I hope that is all making sense so far. Okay. So the way that I'm going to be making this point is to say that in order to achieve the energy efficiency that was required by evolution, cognitive processes in the brain or information processing in the brain would have to rely quite heavily on the specifics of the brain's tissue, so the brain's chemistry. And because of this reliance, in order to achieve efficiency, then it's not going to be to be expected that these processes could feasibly be duplicated in a fundamentally different kind of physical medium. So as a warm-up to this idea that dependence, reliance on the physical properties of the medium is a path to achieving greater efficiency, energy and space efficiency of computation, I'm going to give you this contrast between analog and digital coding, which is an example that I used in an old paper of mine. And it's a warm-up. I'm not going to be arguing that the brain is an analog computer, but this is to give you the principle that's in play here. So this was based on this idea I got is from an analysis by this computer engineer, Sarpashkar, in this paper, where he's comparing the space and energy costs of digital versus analog computing. And the overall message is that analog computing is cheaper, but you get a worse signal to noise ratio. Well, I should rephrase that. What these graphs are showing you is that for a given low range of signal to noise ratios, the analog solution will be the cheaper one. But if you want a high signal to noise ratio, you want very clean computing, digital actually becomes more efficient. And also you cannot achieve the highest signal to noise ratios with analog computations. So given that most engineering applications need very clean signals, need high signal to noise ratios, that accounts for why digital computing kind of took over the computing industry, even though analog computers were, as Corey Maley discusses, actually quite dominant in the earlier 20th century. So why is analog cheaper but noisier? I came up with this example to illustrate the basic point. So if you take one physical medium, in this case, I'm saying one forearm that can be moved at different angles. So one physical component, if you're using it to signal with a digital code, you're restricted in how many bits of information you can signal with this one device. So for the digital code, you need your physical object to switch between two different states, the positive signal cold and the null signal not cold. And this one device is just going to be switching between those two states. That's one bit of information per component. If you take an analog approach, you'll look at your physical device, your forearm, and say, ah, well, it has this interesting property that it can move through a continuum of angles. There are very many different angles that this arm can be placed in. Why don't we use a whole range of angles to signal a whole range of different states of our code? And so this makes the informational richness of this device endless, but limited by the resolution from which you can differentiate different angles. So effectively, it's limited by noise, but the whole physical richness of your device, i.e. the whole continuum of different angles that it can be moved in, can be leveraged in order to signal more information using your code in this analog style way. So the basic principle here is that by looking at more of the physical properties that are there in your object that you're using to code something, and saying, I'm going to extract as much possible code from my medium as possible, from my component as possible, that allows you to reduce the amount of energy and space or materials that you're needing to code the same amount of information as with a digital system. So this is to move to the point that energy constraints were a major factor in the evolution of the brain. So this is uncontroversial amongst both neuroscientists and evolutionary biologists. So Sterling and Laughlin, who I mentioned before in their book, The Principles of Neural Design, sort of begin with this issue that signaling or information processing is an energy intensive business. There's no way to make it absolutely cheap, but having nervous systems is obviously adaptive for the animals that have them, and the bigger the nervous systems, the better. So you want to grow more neurons. Each neuron and the amount of signaling that it's doing, the amount of spiking that it's doing, costs an organism lots of energy. So there will be a quite substantial evolutionary pressure for neural systems to be as energy efficient as possible as they grow. And this is thought to have played out in the history of the evolution of human brains. So one of the arguments about what led to expansion of brain size in hominid ancestors was the use of fire, which meant that tubers could be cooked and therefore release more calories when eaten. So for the same amount of effort going into foraging vegetables like tubers, by taking the same amount of food and cooking it, that released more energy, which meant that people could grow bigger brains. So to move on to this point of how evolution would have achieved signaling on the cheap. So an important point made by Godfrey Smith and then Sao is that you begin with what you have. There's a existing tissue in the body which gets adapted into neural tissue, which means that you co-opt existing molecular pathways that cells are doing anyway. All cells are doing a lot of biochemistry, and you do additional information processing tasks that then get connected to specialized things that nervous systems do, like control of movement. In general, a signaling system is cheap when it works with the existing dynamics of the physical system rather than imposing an independently designed structure. So you think of any physical system, it will have its own inherent dynamics that it will cycle through. If you kind of modify the dynamics or nudge it in certain ways with a small investment of energy, a small placement of a constraint, you can get it to signal something without, and if you're working with the inherent dynamics of the system, you'll be doing that more cheaply than if you're saying, I'm going to take this physical system, regardless of its inherent dynamics, I'm just going to get it to switch between states that I want to get it to switch between, then that will be a more energy intensive way of going about things. Hope that makes sense. And it's cheap when you use as many of the possible pre-existing physical properties that are already there and put them to the service of signaling. So and there's really rich discussion in Rosa's paper from 2022, the South 2022, it really goes into lovely amount of discussion of what the different sort of molecular possibilities are there with neural tissue. And it really does look as if the brain has sort of leveraged as many of those as possible, along with other things like anatomical adaptations with dendrites, sort of the richness of structure, sort of building the architecture in certain ways. You can, it makes perfect biological sense that these were just modifications which were put in place to increase the information coding capacity of neurons without massively scaling up the resource demands, by leveraging as much as possible from the tissue that's there already. The result of this is that the cheap signaling that will have evolved because evolution needed to be thrifty will be highly dependent on the specific physical properties of the medium. They'll be dependent on the arrangement of the hardware, just the spatial arrangement, the anatomy, and it will be dependent on the chemical components that are there in cells. So, unsurprisingly, this leads us to the conclusion that practical medium independence will not have been the route that evolution took with the brain. So any system whose functions, I need to remove this, any system whose functions satisfy the PRAC-MI condition 1 will not be maximizing the information carrying capacities inherent to any particular physical medium. It cannot because it needs to generalize across the media. So that first constraint was that there is a description and an abstraction from the physical system, which is, if you like, high level enough that the causal structure of that high level abstraction could map onto something of a very physical, chemically different medium, and still feasibly be performed. So the greater the extent that the system is maximizing the information carrying capacities of its medium, the narrower the range of variant media will be that can yield equivalent functionality. So the point is that the more efficient you go, the more constrained you are with the materials that can implement that one efficient solution. And so because evolutionary pressure was towards resource efficiency, we should not think that practical medium independence would have been what evolved. One of the arguments that has influenced my thinking on this comes from an old paper by Michael Conrad, who's a computer scientist who is interested in biology. He writes interesting things about the disanalogy between brains and machines. So some of the things that are there in his comparison, you say are kind of obsolete when we're thinking about neuromorphic computation, which is parallel, just like brains are. But I've highlighted a couple of things that are important to my argument here. So he says digital computers need to be programmable. Programmability is interestingly connected to practical medium independence. So when you're thinking about what makes something programmable, like your laptop, it means that the functionality is separate enough from the hardware that you don't need to go around and fuss with the hardware in order to get it to run different programs. With analog computers, you actually do have to go in and fuss with the hardware in order to get it to compute different things. Digital machines have this programmability thing due to the fact that the functionality kind of floats free at this high level of abstraction from the fixed properties of the hardware. But what this means, as Conrad points out, is that there's this low computational efficiency because most of the properties of that physical medium, that is a digital computer, will not be contributing to the performance of the computation. Brains, on the other hand, do not need to be programmable, and they achieve this high efficiency because there's a lot more use of the interactions, the physical processes which are there in the brain that are put towards the demands of information processing. On the top right there, this is making the comparison that I'm emphasizing here, that in a digital computer, the physical realization of the formal system is irrelevant to the computing. Whereas in brains, you have this high dependence of the information processing on the material composition and the physical interactions that innately undergoes. Another sort of reference point to the argument here is Howard Patty and his work on signaling in biology, not just nervous systems, but biology more generally. And he makes this nice observation about the difference between formal symbol systems and symbolism more generally, because he's talking about biosemiotics as a kind of symbol system. So summarizing the idea from him here is that one might see formal symbol systems as a subtype of this more general class of symbolic systems. And the thing about formal systems, this subtype, is that the dynamics are artificially reduced to the point of being inconsequential. So when you're building a machine in order to implement a computation, the formal system of a computation, what you need to do is stabilize the dynamics of the machine so that nothing happens other than the few processes which map onto the steps of your computation. That means the physical dynamics of the machine are largely irrelevant to what's going on. But that's, as he goes on to say, this formal systems require this abstracting from dynamics, which is not necessary in biology. In biology, you're approaching things completely differently. You're not beginning with a formal system, a code, which then you're implementing in a system which you have to build purposely for this. You have this slow adaptive kind of nudging of different dynamics of the system towards different signaling tasks. And that means that the dynamics turn out to be much more code relevant than you would find with a formal symbol system like a digital computer. Okay, maybe I should speed up a little bit so we finish at least my stuff by the hour. So there's an objection that you might already be thinking of to what I've been saying. So don't we see already that artificial neural networks like large language models, computer vision models are already functionally equivalent to brain areas? My reply here is that if you look in detail at the functional capacities of the artificial systems, there are major differences with the functionality of the brain. You can refer to these different kind of cognitive science analyses of artificial neural networks. So I just disagree that we have functional equivalence. I'm not saying that these machines are not really impressive, but I'm saying they're doing something different. And there's this point sort of comes up in this sort of Chalmers style position on in principle possibility of mind uploading. So if you like, a misinterpretation of what I was saying is that, well, you cannot have replication of brain processes in digital machines because brains are chemical and electrical and machines are only electrical. But then the objection goes, but you can simulate chemical signaling in an electrical machine, so there's no barrier to duplicating brain processes in a machine which only does electrical signaling. But that misses the point that I was emphasizing before, that yes, you can do simulations of chemical signaling, but the point is that it is extremely resource intensive to do that in another medium that is not chemistry, and that's why feasibility is the issue here. Yes, in principle, you might say that that's possible, but in practice, you're never going to be able to do that. So yeah, medium independence does not imply practical medium independence. So yeah, just briefly on the implications here, I think I will just restate the obvious point, which is that human-like AGI on digital hardware would turn out not to be feasible. Human-like AGI, i.e. replicating brain processes in another medium, would require synthetic biology, some kind of artificial life. That's not something that the field of neuromorphic computing is interested in at the moment. But it doesn't rule out current AI having intelligence of a sort that's radically different from biological intelligence. I just think we should not ignore the differences. And if we want to call AI intelligent, then we have to be also aware that we're using the word differently in that context. I think I will have to leave the Aristotle bit. If anyone wants to talk about it, the Q&A, we can go back to it. But sorry if you came here for the Aristotle in the title, haven't got to it. I will just leave you with the conclusions and directions. Thank you.